So the keen-eyed of you will notice that I was introduced as Pete, and I am indeed Pete James. I'm not Ovi. Ovi is the author of this presentation, so I'd like to thank him. He's head of our systems team here at Lyra Electronics. As Stephen said, I've just got a short sort of 10 minutes, less than that now, to give you a quick overview of Lyra and what we're doing, the systems and engineering of the OBC, which is an onboard charger. So this device sits on a electric vehicle, and it charges the traction batteries of the electric vehicle from a supply which is off the vehicle, and then a quick summary at the end. So bit of a rush through this, but Lyra was founded 10 years ago, almost to the day. We've got about 37 employees at the moment, and we provide turnkey design for power electronic systems, mainly in automotive, but we do also aerospace and marine. We do all the electronics in-house, so and as you can see there, one of the disciplines we do is systems. So we have a systems engineering team, which is growing like all the other teams, but it's just as important, if not more important, than all the other teams, as we have seen this morning. So one of the first things we do when we take on a new project is we do market analysis. So on the onboard chargers, what's available, what are the trends in recent years, and what is potentially the need, the primary requirements for a new onboard charger. And looking there at standards, so we've got things like the communication protocols that they operate on, voltages. So there's a big move towards 800 volts now by the OEMs in the automotive industry. So we're looking at the output voltage there, and whether you're using single phase or three-phase power supply. So all these sort of things come into the market analysis. Just trying to move forward. There we go. And then we do our use case and functional decomposition. And so there we're looking at the sort of inputs to the system. So the EVSE is the electric vehicle service equipment. So that's essentially the charging unit on the wall that provides the AC supply. We have the VSC, which is the vehicle system controller. So this is the computer that's on the car, which will also communicate with our onboard charger. And then on the right hand side, I'm just going to I had a menu blocking on the right hand side. We have the HV battery, and so that's our output that we're communicating with. And as you can see, there are the main functions that we need the onboard charger to complete. We then group those functions. So the power electronics engineers look at what the functions are and what parts of the product are going to carry out those functions. And we've grouped them together that our onboard charger will have three main functions. It'll have the controller, which is my microprocessor, which will do the communications. It will have a power factor control unit, which is some power electronics, which will manage the power factor of the unit. And then we have a DC to DC converter, which is actually doing the control of the voltage and current to the high voltage battery, and also isolate the battery from the grid. We carry out an initial boundary diagram, looking at the links between each of our blocks that we've identified from the decomposition stage, and we then update this. So it's a fluid a diagram that's updated throughout the process. And as you can see there, we've added the low voltage power supply. So not only does this onboard charger operate off a power supply which is external to the vehicle, the charging point, but it also has to be powered off the internal supply of the vehicle as well, the low voltage supply. We then look at each of the interfaces between each of those blocks, and we identify the measurables as part of, from the interfaces. And what we've done here is we've just looked at the AC power one. So as you can imagine, there'll be hundreds of these for something as complicated as an onboard charger. But if we're looking at the AC power, so this is the interface that the onboard charger is connected to the EVSE, the charging point electronics and the supply. We have things like maximum current, voltage and voltage range, maximum power and minimum power factor. And so some of these functions are a prerequisite from the charging point. Some are a standard that's required depending upon whether you're in Europe or the States or wherever, and others are like the voltage. They have a nominal range, but then there are noise factors where you know, you may have a number of charging points in a car park, and one of the charging point at the end will get a lower voltage if suddenly several cars all appear at once, or maybe there's a foundry close by, and when it switches on its furnaces, the voltage drops slightly. These are noise factors which are outside the influence of the onboard charger, but the onboard charger has to be able to react to them and cope with them. We do an initial P diagram, and again, we're looking at the AC power here, and we look at the noise factors and the ideal outputs, and this gives us the error states of that particular system function. And so the error state here is if we don't get enough power from the charger, then sorry, the charging supply, then the error state is loss of function, the function being the ability to charge the battery. We then generate the requirements through an FMEA, where we're looking, and we rank these with occurrence and severity and so on. And as you can see here, 1.1.3 has said that we've identified that there's a possibility that the components inside the onboard charger would overheat, and this would provide loss of function. And what this means is that we actually need to measure the temperature of the components, and we need to do some derating, or we need to send a message to the vehicle to say that we can't charge any more, and the charging session has to stop. And we then go back to the boundary diagram, now adding in here, you can see A4 cooling plates appeared. We've now got the liquid cooling system, which is outside of our onboard charger, but is part of the vehicle. It's another interface. And so we now have more links. We've got the heat links as well as material exchange. And we then go back through the whole process again to identify all the interfaces and all the functions and so on for these new parts of the boundary diagram. And then, as you can imagine, after a few iterations, the P diagram gets much more complicated, a lot more information in there. And we go around this loop several times until everything is covered. So it's a very, very quick overview of just one aspect, really, of developing an onboard charger. This would take several weeks and a team of people to carry out. But essentially, that's how we use system engineering in the case of an onboard charger to ensure that it meets all the requirements and that we've covered all the interactions with all other parts of the vehicle and the infrastructure connected to the vehicle.